This video covers the alignment of the Quantum Optics Educational Kit up until the measurement of G2 to prove the quantum nature of the photon pair source. In this video, we assume that the blue pump laser has already been properly collimated and that the first optical elements in the pump laser's beam path were placed on the breadboard as described in the manual. Next, we add the alignment laser and the two mirrors that allow us to couple the alignment laser into the beam path. First, make sure that the alignment laser is horizontal by placing an iris with a fixed height 50 centimeters away from the laser and correcting the beam angle. Next, place the laser on the breadboard as shown here. Position the first mirror so that the laser beam is incident on the center of the mirror and the light reflects at a 90-degree angle. Proceed similarly for the second mirror, which is mounted on the magnetic plate. Place the ID25 iris close to the mirror. We will call this iris the alignment iris. Next, place the beam trap at the opposite end of the breadboard from the alignment iris. Use the beam walk method to tip and tilt the two kinematic mirrors in the alignment laser's beam path until the beam passes through both the alignment iris and the beam trap iris. Tip and tilt the first mirror to center the beam on the alignment iris. Next, tip and tilt the second mirror to center the beam on the beam trap iris. You may find it helpful to open or close each iris, depending on where the spot from the laser beam is. Repeat this process until the laser passes through the center of both irises. As you can see, several iterations are usually needed for this step. More details on the beam walk method can be found in our How to Align a Laser Insights video. When you have finished using the beam walk method for the red alignment laser, switch off and remove the mirror mounted on the magnetic plate. Next, repeat the beam walk method for the blue pump laser. Attach a piece of white paper to the viewing screen. The bleach in the paper emits fluorescent light, which helps us see the laser spot even with laser safety glasses on. Put on the provided laser safety glasses and switch on the pump laser. Tip and tilt the mirror closest to the laser mount to center the beam on the alignment iris. Seeing the 405 nanometer laser on the black iris blades is difficult. Therefore, it is easier to observe the screen placed behind the iris. You may find it helpful to open or close the iris, depending on where the laser spot is. Use the second mirror to center the beam on the beam trap iris. To do so, unscrew the SM1 threaded end cap and observe the screen placed behind the iris. Repeat these steps until the pump laser passes through both irises. You have now ensured that the alignment laser and the pump laser are collinear. Switch off the pump laser. Screw the SM1 threaded end cap onto the beam trap iris. Place the magnetically mounted mirror back into the alignment laser's beam path by gently sliding it onto the magnetic base. Place the Axicon in the beam path with the kinematic adjusters facing away from the alignment iris. Switch on the alignment laser. Most likely, the Axicon pattern will not be evenly bright. First, adjust the height of the Axicon. To ensure normal incidence on the Axicon, observe the back side of the alignment iris. Tip and tilt the Axicon to ensure that the reflected beam is directed back through the iris. Double-check the height by making sure the Axicon pattern is evenly illuminated. You may need to fine-tune the height and the tip tilt to ensure an evenly illuminated pattern and that the light hits the Axicon at a normal incidence. Remove the Axicon. Place the fluorescent alignment tool into the beam path and set the height so that the laser passes through the hole in the center. Return the Axicon to the setup by gently sliding it onto the magnetic base. In the following steps, we'll coarsely align the detector. This means that we'll add the single photon detectors to the setup and make sure they are oriented in the right direction. Place the fluorescent alignment tool into the Axicon pattern so that laser light passes through the hole in the center. Place one of the detectors in the setup close to the beam trap. Take the 1-inch economy beam splitter that is mounted in the short lens tube and screw it onto the detector's dovetail adapter. Position the detector so the laser spot is centered on the diode. Adjust the height of the detector. The beam splitter reflects half of the light back to the fluorescent alignment tool. Rotate the detector until the reflection is directed back through the hole in the alignment tool. It is crucial to repeat this sequence of steps until the beam is both centered on the detector and the reflection passes through the hole in the alignment tool. Again, make sure the laser is still centered on the diode, then check the reflection, and so on. Secure the detector to the breadboard and remove the economy beam splitter from the first detector. Repeat the same procedure with the second detector. Move the fluorescent alignment target to the other side of the alignment laser light cone. Screw the economy beam splitter onto the second detector. Adjust the height and position of the detector until the laser spot hits the diode. Make sure that the reflected light passes back through the hole in the alignment target. You may see two reflections on the back side of the alignment target. In that case, one is from the economy beam splitter while the other comes from the material surrounding the diode. The brighter reflection comes from the beam splitter and is the one that is supposed to pass through the hole in the alignment target. Confirm that the laser is still centered on the diode. Secure the detector to the breadboard. Switch off the alignment laser. Remove the economy beam splitter and the alignment target. Connect the detectors to their power supplies. Also connect the SMA output of the detectors to the time tagger. Make sure that the outer detector is connected to the first input connector of the time tagger. You may add the sticker with the letter T next to this connector, as this is what it is called in the software. Place the detector optics assembly onto the first detector. Make sure that both the zoom housing as well as the XY fine adjusters are in the middle of their travel ranges. For the fine adjusters, ensure the white markers are collinear. For the zoom housing, rotate it to either end of its travel range and then reverse by about half a rotation. Finally, open the detector iris completely. Repeat this process for the second detector. Replace the AXCON with the colored glass filter. Remove the magnetically mounted mirror. Switch on the pump laser. Make sure to use a diode current about 5 milliamperes below the laser threshold, as otherwise the detector will saturate. The purpose of the glass filter is to fine-tune the lens position in the detector optics assembly. The colored glass filter's fluorescent light comes from the exact point in space where the photon pairs will be created within the BBO crystal later on. The detector lens position is now fine-tuned so that the light collected from this point in space is maximized. Even if no or little 810 nanometer light is present in the room, you may need to dim the lights to ensure that you find the signal. Turn one of the adjusters and observe the detector count rate in the kit's software. If the count rate goes up, keep turning the adjuster. If the count rate goes down, turn the adjuster the other way. Do so until you reach a local maximum. Repeat the step with the other adjuster. Rotate the zoom housing to move the lens closer or further away from the diode. Again, turn the knobs back and forth and rotate the zoom housing. Repeat this series of steps as many times as needed to ensure that you find a global maximum and not just a local one. Repeat the same steps for the second detector. Once you have maximized the count rate for the second detector, switch off the laser. Place the alignment mirror in the setup and replace the colored glass filter with the mounted BBO crystal. Switch on the alignment laser. Now, tip and tilt the BBO crystal in its mount until the reflection is directed back through the center of the alignment iris. thereby ensuring the perpendicularity of the crystal with respect to the optical axis. Switch off the alignment laser and remove the alignment mirror. Next, we will change the angle of the BBO crystal, which changes the opening angle of the photon pairs. Switch on the pump laser. Set the coincidence window to 20 nanoseconds in the Delay Adjust tab. Choose the diode current to achieve about 13 milliwatts of output, based on the laser diode spec sheet. In our case, that's about 31 milliamperes. Slowly actuate the lower knob of the BBO crystal's mount and observe the count rates. Once you have maximized the count rates, observe the coincidence count rate between detectors T and A, which is shown in the lower graph. The system is quite robust. You can remove and gently replace the BBO crystal, and you will still see your signal. Switch off your pump laser. Switch to the Delay Adjust tab of the software and set the coincidence window to 5 nanoseconds. Use the default settings in the software and press the Start Measurement button. The measurement shows the actual time delay between the detectors, which can be caused by electronic differences and delays between the detectors, as well as runtime differences caused by different distances between the crystals and the detectors. There should be a peak with a full width at half maximum of about 5 nanoseconds. Drag the blue vertical line to estimate the delay value at the peak center. In our case, we find a delay of about 0.2 nanoseconds. Enter this value into the Delay A to T field. Place the alignment mirror in the setup and replace the BBO crystal with the Axicon. Switch on the alignment laser and place the fluorescent alignment tool in the laser light cone. Place the beam splitter with the open iris in the system. Watch the backside of the alignment tool and carefully rotate the beam splitter until the reflection from the beam splitter passes back through the hole in the alignment target. Check that the laser is still aligned to the center of the beam splitter iris by closing it. If you need to move the beam splitter slightly, be sure to verify that reflection still passes through the hole in the alignment tool. Don't forget to open the beam splitter iris afterwards. Screw the economy beam splitter onto the third detector. Place the detector so that there is about equal distance between the beam splitter and detectors 2 and 3. Place the fluorescent alignment tool in the path of the reflected beam. Set the detector to the correct height and rotate it until the light both hits the diode and is directed back through the hole of the fluorescent alignment tool, as you have already done with the first 2 detectors. Secure the detector to the breadboard. Remove the economy beam splitter and the alignment tool, and switch off the alignment laser. Connect the detector's SMA output port to the third SMA connector on the time tagger. Also connect the detector to its power supply. Replace the Axicon with the colored glass filter and remove the alignment mirror. Like before, make sure that both the zoom housing as well as the XY fine adjusters, are in the middle of their travel range. To do so, ensure the white markers are collinear. Also, rotate the zoom housing to either end of its travel range and then reverse it by half a rotation. Attach the detector optics assembly to the third detector. Switch on the detector and wait until the detector indicator LED turns green. Then, turn on the pump laser, again at 5 milliamperes below the laser threshold. Actuate the adjusters and the zoom mechanism like before to find the maximum count rate for the third detector. Make sure to fully open the detector iris. Show the count rates of all 3 detectors by clicking on the T, A, and B buttons at the top right of the upper graph. To ensure that the count rates are optimized to the actual signal and not environmental effects like stray light, switch off the blue laser. There should be a sharp drop in both individual detector counts as well as coincidence rates. Switch off the pump laser and replace the colored glass filter with the BBO crystal by gently placing it onto the magnetic base. Switch the pump laser back on and set a diode current to a value corresponding to about 13 milliwatts, in our case, about 31 milliamperes. Go to the Delay Adjust tab and set the coincidence window to 20 nanoseconds. Slightly actuate the lower knob of the BBO crystal's mount and observe the count rates to make sure that the maximum count rate of the third detector occurs at a similar screw position compared to the other 2 detectors. If the screw position of the maxima are significantly different and no coincidences are observed, repeat the procedure for positioning the third detector. Switch to the Delay Adjust tab and set the coincidence window back to 5 nanoseconds. Use the default settings in the software and start a measurement. In our measurement, we estimate a delay of about negative 0.5 nanoseconds for the third detector. Enter this value into the Delay B to T field. Go to the Alignment tab. You should now see a similar coincidence count rate for T and A and T and B in the Alignment tab. You may notice a drop in coincidence count rate due to the shortening of the coincidence window from 20 to 5 nanoseconds. Select the GRA tab of the software, choose a measurement time, 20 seconds is recommended, and start the measurement. This will display the count rates, the absolute counts, and the calculated G2 values. With good alignment and sufficiently good lighting conditions, this value will be below 0.1. This value proves the quantum nature of the light source. Congratulations! You have aligned your quantum optics educational kit.